All right, I just want to do one more example of a bond dissociation energy to estimate the delta H of a reaction, just so you guys are sure to get enough practice at it. So if we have this reaction here, methane, CH4 gas, plus 3 Cl2 gas, gives us CHCl3 gas, plus 3 HCl gas, and we want to know what our delta H is. Well, just like in the last problem, the very first thing we need to do is a Lewis structure for all of these molecules. CH4, simple, one bond to each carbon. Cl2, also simple, single bond, 3 lone pairs. And I am going to draw out every single molecule because I don't want to miss one. And you do need to draw out the Lewis structure because if you get the Lewis structure wrong and the wrong type of bond in there, it's not going to work. And then we get the CHCl3. That's pretty simple too. And finally, we have that HCl. And we have 3 of those. Again, just a single bond here. All right. So now remember that we're breaking all of these bonds. We break these bonds and we form all of these bonds. And some of you may have picked up on the fact that we have carbon-hydrogen bonds over here and we still have this carbon-hydrogen bond over here. Do we really need to worry about that? It's just easier to do all of the bonds. It ends up canceling out in the math, but like I said, just simpler to do it all, okay? So our delta H is going to be equal to 4 times the bond dissociation energy or the bond energy for carbon-hydrogen because methane has 4 carbon-hydrogen bonds. And we have 3 chlorine-chlorine bonds. So that's the bond energy of a chlorine times 3. Minus, I'm going to put this whole side in brackets. Now, on this side we have 1 bond energy for carbon-hydrogen, or hydrogen-carbon again, doesn't matter, plus 3 bond energies for carbon-chlorine, plus 3 bond energies, let's do that in the green, 3 bond energies for a hydrogen-chlorine bond. And I put that in brackets because of that minus sign out there, okay? Because we want that to distribute all the way through. So if we go ahead and substitute values in here, we have 4, and I'm going to kind of be a little bit loose with the units, 410 kilojoules, because I don't really want to, I'm even going to be looser with the units. I'm going to do this, I'm going to put the units at the very end because it's all just kilojoules. Plus 3 times 243 kilojoules. Like I said, I'm being kind of loose with the units just because I don't want to write them over and over and over again. 1 times 410 plus 3 times 330 and plus 3 times 432. Okay. Now it's important in this type of problem to get it all set up correctly. Sometimes you'll end up making an error somewhere along the lines, in terms of your math, your arithmetic. That's all right. Just get it set up correctly. I can give you partial credit. And I did put the unit outside because this whole thing, we can just say the unit for that whole calculation is kilojoules. Okay. And when I do the math on it, calculate the answer, I get negative 327 kilojoules. Now I didn't bother to go back and actually look up this reaction, but I think we can say that's a fairly good estimate. And that does it for chapter 10. There is no more videos for chapter 10. I know you're sad, but don't worry, we'll pick it up with chapter 11.